All right, in this video, we are going to talk about graph realization. So, in the last lesson, we talked about the degree sequence of a graph, and that is the sequence formed by arranging the vertex degrees in non increasing order. There was a typo I had, non decreasing, right, in the previous video in this spot right here, but it's non increasing. The numbers stay the same or go down. Okay. So you would find the degree of each vertex, get all those numbers, and then range them in a sequence, right, from the biggest to the smallest. And, oops, sorry. All right, let me fix that for a second. Just bear with me. Okay. So one question that you could ask is: given a sequence of non-negative integers, um, is there a graph whose degree sequence is precisely that sequence? Okay. Again, you would have to rearrange it in non-increasing order. Okay. So a sequence of non-negative integers is called graphic if there exists a graph whose degree sequence is precisely that sequence. Okay. So what we want to do is just look at the degree sequence and figure out whether or not there is a graph with that degree sequence. All right, so there are some pretty quick ways of determining whether a sequence is graphic. They don't work in every case, and so, but if I have a sequence of non-negative integers, right, and just assume that they're in the non-increasing order, and we want to be able to determine if that sequence is graphic, right? Then there is a number of things that we can check based on this on these criteria here. So if a degree sequence is graphic, then the sum of the numbers in the degree sequence has to be even. So if you add up all the numbers in the degree sequence, that has to come out to be an even number. The number of odd degree vertices have to be even. And the sequence must have a repeated number if the length is greater than 1. And the length of the degree sequence must be at least 1 greater than the first number in the sequence. Okay. So we'll take a look at each one of these things in turn and see why these are true. Okay. So let's just remind you of a little bit of logic, details on logic here. So if the degree sequence does not have one of these properties mentioned above, then the sequence is not graphic, right? And that just comes from the contrapositive of this statement here, right? If one of these is not satisfied, right, then it's going to say that the degree sequence is not graphic, okay? So that's an easy way to tell if a degree sequence is not graphic, doesn't satisfy one of these. If a sequence has all of those properties mentioned in the conclusion of that theorem, right, it does not mean that the sequence is graphic. All right, so make sure that just because it satisfies all these does not mean that it's graphic. If I give you a degree sequence and it satisfies all of these properties, right, then you're going to have to resort to another means of determining whether or not the degree sequence is graphic. Okay. So, and that is the Havel-Hakimi algorithm. That will tell you, running through that algorithm, right, you'll go through a set of steps, right, and at the very end you will get a simpler sequence. And that simpler sequence will tell you if it's easy to, or if the sequence is graphic or not. All right, and so we'll go through all that. So again, just make sure that you understand the logic here. That's important. Right? failing to have one of those properties means that the sequence is not graphic, right? And it does not necessarily mean if a sequence has all of those properties, it doesn't mean that the sequence is graphic. Okay. So in terms of the sequence, right, if I add up all the numbers in the sequence, it has to be even. There have to be an odd number. There has to be an even number of odd numbers in the sequence. Sequence has to have a repeated number, and the length of the sequence must be at least one greater than the first number in the sequence. All right, so let's talk about each of those things. All right, first off is the sum of the degrees. Check to see if the sum of the degrees in the sequence is even. Okay, so this goes to theorem 1.1.1 in our book. It says let G be a graph with p vertices, and let d1, d2, d sub p be the degrees of the vertices respectively. Let q be the number of edges of G. Then d1 plus d2, the sum all the way out to dp, is equal to 2 times q. All right, so the sum of the degrees is twice the number of edges. All right, so what that means, right, this number over here on the right-hand side is 2 times some other integer, right? And so therefore, that means it's even. And so therefore, since the sum of the degrees is even, right, then we know that that if you sum the numbers in a degree sequence, which is what this expression is, that you will come up with an even number. All right, and the idea behind that is just that if you count up the degrees, let's see if I have a graph looks like this. Right, the degree here is 3, the degree here is 1, 1, 3, 1, 1, right? So whenever you're counting that up, what you're doing is counting the edges, right, that are going into each vertex, right? So here, this edge, and this edge, right? And then you're adding those things up, all right? And since an edge, right, is in a regular graph, or just graph, right, is determined by 2 vertices, when you do that, you're counting each edge twice, right? So for instance, here I count this edge, and this edge when I do the 3, right? Then I count this edge here, so that counts this edge here. So you can see that one's been counted twice when I do the +1. Next, I add this one, so that means I'm counting this edge a second time. Then I'll do this vertex, and so that would count this edge for the second time, this edge for the first time, and this edge for the first time. Then this +1, so I'm counting this edge for the second time, and then finally this vertex. You can see I'm counting that vertex for the second time. So by adding all of these numbers up, right, you come up with you are counting every edge twice, and just verifying, right, when we add all this up, we get 1, 2, 3, 4 plus 6 is 10, right? And the number of edges, 1, 2, 3, 4, 5. All right. So that's pretty much it as to the reasoning behind that theorem, right? Here I'm counting every edge twice because every edge is determined, by exactly 2 vertices. Okay, so that tells us, right, that say this sequence right here is not graphic, right? If you add all those numbers up, right, that's 9, 13, 15, 17, 19, 20, 21, right, is what that adds up to. So this sequence is not graphic. There's no way that you could come up with a graph that has this degree sequence. All right, the next criteria that we talked about in the list was the number of odd degrees. All right, and this way is actually a little bit faster than the previous way, right? And this is exercise 1.15 in our book. It says in a graph, the number of vertices of odd degree is even. Okay, so for instance, this sequence is not graphic, right? Because I have 1, 2, 3 vertices of odd degree, and so this theorem says that there has to be an even number of odd degree vertices. Right? And the idea behind this one is also really pretty straightforward, right? Because if I add up all of these degrees, right, if I add any number of even numbers together, right, I am going to get an even number, right? 4 plus 4 plus 2 plus 2 plus 2, right? It's going to come out to be even. Then when I start adding odd numbers together, right, the parity is going to change. 5 plus 1 will give me 6, right? If you add two odd numbers together, you are going to get an even number. And then if you have an odd number of odd numbers in there, that's going to flip it to 1. 6 plus 1 is 7, right? Because an odd plus an even is odd, right? So the odd numbered vertices have to pair up, right, to make an even number, because we know that the sum of the degrees has to be even. Okay, so that's actually a little bit faster check than adding up all of the degrees there. Okay. All right. The next criteria that we talked about was that the degree sequence of a graph with more than one vertex has to have at least one repeated number. Okay. So if you only have one vertex, right, then the sequence is just the number 0. So that doesn't have a repeated number. But if you have more than one vertex, right, then you have to have at least one repeated number in there. All right, and so for instance, this sequence right here is not graphic, right? 7, 6, 5, 4, 3, 2, 1, 0. All right. So how does this work? This is exercise 1.17 out of her book. All right, so the idea here is, right, you have your degree sequence and whatever the largest number is, right, 7. So that means that this vertex, that means that this vertex has degree 7. That means that there have to be 7 edges coming out of it. 1, 2, 3, 4, 5, 6, 7. All right. So there are 7 other vertices coming out of it. All right, and so now if you look at the other numbers in the degree sequence, it's 6, 5, 4, 3, 2, 1, and 0, right? So, this one might be the one with 6, and there's some other vertices coming out of it, which I'm not going to draw all of them. This might be the one with 5, so there's other edges coming out of it. So this one might be the one with 4, so there's some other edges coming out of it. This one, right, might be the one with 3. This one might be the one with 2, right? And this might be the one with 1, but that leaves 0, right? So here. And so since there's already an edge, right, coming from this vertex of degree 7 out to this one with 0, this one already has 1, so you can't have that, right, in there. So that's the idea behind it. Whatever the largest number is, right, you're going to have at least that many vertices So this one is 7, right? So that means I have to have at least 7 other vertices, and there they are, right? Those numbers are all going to have to be different. So they're going to have to be 6, 5, 4, 3, 2, 1, 0, right? And so that means that 0, 1, there can't be an edge coming from the 1 here, but there has to be, right? So you can't have that. There has to be at least one repeated number, okay? So that's the idea behind that exercise. All right, sort of related to that is the length of the sequence, right? The length of the sequence has to be at least 1 greater than the first number in the sequence, right? So for instance here, the biggest number in the sequence was 7. That means there have to be 7 other vertices, right, to follow it, because this vertex has edges to all of the other vertices, right? So there have to be at least 7 to go to, and one of them can't be 0 either, right? So in this particular case, right, here I have the first and the largest number is 8. That means there need to be 8 other vertices in here, because we're not talking about multigraphs, right? There have to be 8 other vertices in here, and you can see there's just not, all right? So there's no way that this could be the degree sequence of some graph, okay? All right, so those are the criteria, and those are the easy checks. If you have some degree sequence, you should check those, right, and see what, if the graph doesn't satisfy that, then boom, you can immediately say it's not graphic because, whatever, whichever one of those reasons pertains to it, okay? All right. So those are the quick checks, right? And what do you do then if a graph has all of those? Well, then you resort to this algorithm, the Havel-Hakimi theorem, and the corresponding algorithm, right, which is just a set of steps that are associated with the algorithm, or with the theorem here. So, so it says, consider the following 2 sequences and assume sequence 1, this one right here, is in descending order. So here I have a degree sequence, right? And so here, whatever the first number is in that sequence is called S, right? So S will be the biggest number in the sequence. So for instance, in this example, it's 5, right? So S would be 5 here. And then I have at least 5 vertices that follow it, right? So T1, T2, all the way out to TS. So in this example, T1 is 4, T2 is 4, T3 is 2, T4 is 2, and T5 is 2. All right, so that is the S number of S vertices that follow. And then you have some other vertices that are beyond that, possibly, right? Okay, so 1 and 0 in this case. So you're starting with a sequence that looks like that. All right, and then it says if that sequence is graphic, right, then this sequence 2 has to be graphic. And so sequence 2 you get by first chopping off the first number, right? So this would be chopped off. And then you would subtract 1 from each of the T sub i's. So this 4 would become a 3, this 4 would become a 3, this 2 would become a 1, this 2 would become a 1, and this 2 would become a 1, okay? And then the D sub i's are just left, right? You don't do anything with them. All right, so this sequence, right, you can see I start with this sequence. If I apply that operation, it results in a shorter sequence with smaller numbers, okay? So that's part of what it says. And so it's easier to tell if this sequence is graphic than this one. Now, likewise, it says if this sequence is graphic, right, then this sequence will be graphic as well. If I identify some number 3 or bigger, whatever the biggest one here is, the next number that I'm going to add out in front needs to be larger than that, right? Actually, it has to be 4 in this case, but so if I add, or actually if I just pick some numbers here, right? It doesn't matter how many. So sorry, you just pick however many you want to, right? And then add 1 to those. So in this case, it was, I picked these right here. Actually, these right here. And I add 1 to all of those. So you pick some number of the first vertices that you have. Add 1 to all of these, right? So this one becomes a 2, this one becomes a 2, this one becomes a 2, this 3 becomes a 4, and then this 3 becomes a 4. And then however long this sequence is, right? 1, 2, 3, 4, 5, you add that number out in front. And then you might have to rearrange it in descending order. Okay, that's the only trick. Okay, then so if you do that operation backwards, you'll get another more complicated degree sequence. And the theorem says that those two sequences, or sequence 1 is graphic if and only if sequence 2 is graphic. So that, remember from the logic, that implies that if sequence 1 is graphic, then sequence 2 is graphic. And if sequence 2 is graphic, then sequence 1 is graphic. All right, so the idea, what we want to use this for, is to take a complicated sequence, degree sequence, right, and reduce it down to a simple degree sequence, and so that it's easier to tell if the simple degree sequence is graphic, right? At the very end, you'll be able to see pretty easily whether or not it's graphic or not. And then if the sequence that you wind up with, the simplest one, is graphic, well, that means the original one is graphic. And if the one you wind up with is not graphic, then the original is not graphic either. Okay? So that's the idea of it. Going backwards from the very simple one sequence to the more complicated one gives you sort of an algorithm for drawing a graph given a degree sequence. Okay, and we'll talk about that later. All right, so let's see how to actually put this into practice. All right, so I think this is the one that we looked at before, and here are the steps. I'm going to write this down, and then we can go through all of these steps one by one. All right, so these degree sequences 5, 5, 4, 4, 3, 2, 2, 1, and 0. All right, let me just double check that. 5, 5, 4, 4, 3, 2, 2, 1, 0. Okay. All right, so the first thing that we want to do here is look at our first number is 5, right? So we would look at the t sub i's and identify those. So that would be 1, 2, 3, 4, 5. Right here. Okay. And then what we would do is pop off this first number and get rid of it, and then subtract 1 from all these. So this would be 4, 3, 3, 2, 1, 2, 1, 0. Okay. So that's what our sequence looks like, and then we're going to have to reorder it, right? Because it's not in non-increasing order anymore. All right, so we have 4, 3, 3, 2, 2, 1, 1, 0. All right, so next, and keep doing this. All right, so next up, follow the same steps here, right? We look at the first number, that's 4, right? So we want to look at the next 4 vertices after. All right, those are our t sub i's. All right, and then what we want to do is we get rid of this first one, and then we subtract 1 from each of the others. So we wind up with 2 2s, 4 1s, and a 0. All right, we don't have to reorder this one. Everything's good with that. And so Keep going. So here our S would be 2, and so we would have these two are T sub i's and these are others. All right, and then we would pop off the 2 and subtract 1. All right, this time we're going to have to reorder. And that should be a 0. Then we would keep going. Here's our S, right? And so we would look at the next 1 vertex, right? And then subtract 1 from all those and keep the rest. Reorder. Keep going. So our S is 1 again. So we would look at this next one, subtract 1 from it, and pop off that 1 there. So we wind up with 0, 0, 0, 0. All right, and here we've wound up with all zeros, right? And it is very, very easy to draw the graph of this graph with this degree sequence, right? Because we would just have 1, 2, 3, 4 vertices. So there's your graph. Very easy to tell, right? If you have all zeros in here, that it is graphic. Okay. So that means this one's graphic, right? So is this one, so is this one, so is this one, all the way back at the chain. So we know that this is graphic, okay, up here. All right, so that's the idea of the Havel-Hakimi algorithm. All right. Let's take a look at the next one. And by the way, I'm pretty sure that this satisfied all the others. You should, I didn't check because I knew that it was going to come out right, but you should check the others first, you know, the other conditions that we talked about, unless you just like doing it this way. Okay, next example. Let's take a look at that one again. All right, I'm going to erase that one. And we will go with this one in the next example. All right, so here I have 6, 6, 5, 5, and then 4 2s. 1, 2, 3, 4. I wrote that lower than I wanted to, but it's probably okay. All right, so so the question is it graphic or not, right? So again, we'd identify S is 6, so we'd look at the next 6 vertices after that. Those are our T sub i's, right? And this is our D sub I, as it's denoted in the theorem. So we would pop this first one off, right, and subtract 1 from all these. 4, 1, 1, 1, and then a 2. That one we're going to have to reorder, right, because it is not in non-increasing order. All right, and then now our S is 5, so we look at the next 5. 1, 2, 3, 4, 5. Pop this one off. That's going to be 3, 3, 1, 0, 0, 1. Reorder. Okay, now we look at the next 3. right? Our S is 3, so we would look at these and subtract 1 from these. Pop the first one off, so we get 2, 0, 0, 0, 0. Okay, so now when we've are at this point, right, we can see that our S would be 2, right? And so we would have to subtract 1 from each of these, right? But that's not possible to do, right? Because that would put us into negative numbers, right? If we subtracted 1 from these two. And so you can't have negative numbers in here. 0 is the smallest number that you can have. So if you come to a point where, you know, doing the next step in the algorithm would make one of your numbers go negative, then it's over with, okay? And so looking at this degree sequence, we can see, right, that there's no way any graph could have this degree sequence, right? Because of the fact you're going to have 5 vertices. That's easy enough to do, right? But you can't have one with degree 2, right? That would mean there's going to be 2 vertices coming from this one. Well, where are they going? They can't go to any other vertices, right? So these 2 edges coming out of this vertex, if they went to any of the other vertices, well, they wouldn't be 0. So there's no graph with this degree sequence right here. All right, so that means that this sequence is not graphic, this sequence is not graphic, this one's not graphic, this one's not graphic, and so the original one is not graphic as well. All right. Okay. So that's the Havel-Hakimi algorithm, right, in theorem. So this is what you want to go through if you check all those other conditions that we mentioned first, but if none of those work, then this is what you're going to go through and reduce this down, okay? And then again, you just kind of look at this. These ones should be really easy to tell whether or not it's graphic or not, okay? So, like I said, this also, if you use this this algorithm, it will allow you to draw a graph with a given degree sequence in a pretty straightforward manner, right? You may say, well, look, it's really not that hard to draw this degree sequence or a graph with this sequence right here, and it's probably not, right, that hard for this particular one. But if you kind of go back through this in reverse, it gives an actually pretty easy way. Like if you had a more complicated graph or something like that with a longer number of vertices or whatever else, you could follow back through this algorithm in reverse to generate a graph with that given degree sequence. Okay, so I'm going to show you how to do that. So here is the reduction for this particular sequence, right? So here I would our S is 4, right? So I'd subtract 1 from these 4. So that gives me a 1, a 1, a 0, and a 0. And then I have my S is 1, so subtract 1 from here and pop that off. And this gives me the 4 zeros, which we already know is graphic, right? That's a graphic sequence. All right, so you would start here at the bottom if you're reconstructing this. So draw a graph, right, that has this degree sequence, and so it's just 4 isolated vertices. All right, and then to go backwards, right, the next step above it was 1, 1, and then 3 zeros, right? So what you would need to do is draw one vertex, right, another vertex right here of degree 1, and then you would just draw an edge to one of those vertices, like so. So the red vertex and edge are the new things that we added in there. Okay. So going from here, right, you would draw a new vertex, right, and then you would connect that new vertex to one of these vertices right here. All right, so that's what it would look like. And then the next step back up. All right, and the next step up, right, it was 4, right, was added out in the front. So that there you would pick, right, a new vertex and add that in there. So here's the new vertex colored in red. And then what you would do is draw an edge from that vertex to these four vertices right here. So draw it from an edge from F to one of the vertices of degree 1. Draw an edge to the other vertice of degree 1. And then draw an edge from F to one of the vertices of degree 0. So you can see I've done that here. And then draw an edge to a different one of the vertices of degree 0 right here. All right, and that's it. So that's pretty much what you have to do. Just look at the next sequence up, right? And then look at the degree. You add a new vertex each time. You look at the degree that the vertex is supposed to be, and then you connect it. Like in this case, it's 1, so you will connect it to the next 1 vertex in the sequence. And same thing here. So in this step up, I added a new vertex, right? And then I'm going to connect it to the next 4 with edges to the next 4 vertices. So I would have an edge from F to a vertex of degree 1, another vertex of degree 1, another vertex of degree 0, and another vertex of degree 0. And you can see that increases by 1 each time, right? The vertex of degree 1 became 2. These 2 vertices of degree 0 became degree 1 because I added that edge inside there. All right? So that's a systematic way in which you can draw, for a graphic sequence, you can draw the graph with that degree sequence. Okay, use the Havel-Hakimi algorithm, and then just follow it back up to sketch the graph. Okay. All right, so I think that is it. Yes, for this video, I want to, in the next video, talk about the proof of theorem 1.1 about the Havel-Hakimi theorem. I'm not going to go through the formal proof. You're going to see that in the you can read that in the textbook, but I will talk about the ideas behind the proof. And it's not like I don't think the formal proof is important. It absolutely is important. If you're going to grad school for math, then you absolutely will be writing proofs, and in fact, that's pretty much all you'll be doing. So, so it absolutely is important, but also understanding the ideas behind the proof are important as well. So you can see how they formalize the proof here, right? So in the next video, I will talk about the ideas behind this theorem.